I'm very pleased to introduce Sihao Chen, who is a PhD candidate from the University of Pennsylvania working with Dan Roth. He works on NLP aimed at providing more intelligent, contextualized, and trustworthy information access. So take it away, Sihao.
All right. Thanks for the introduction, Doug. So today, my talk is going to be a brief overview of my PhD work, which had the theme of towards a more contextualized view of the web. So throughout the presentation, I'll be happy to take questions, but one technical issue is I don't have enough monitors to actually see the Google Meet page. So I think I'll hear like notifications, but apologies ahead if I miss it. But I'll pause in between sections to take any questions. All right. So a little bit more about me. I'm a fifth-year PhD, hopefully final year PhD at UPenn. I work with Dan Roth, and I'm going to talk about my research. But outside of work, I'm a big fan of water sports. So here's a picture of me sailing on Lake Union right outside the AIT office last summer, which was really fun. All right, so I will start by mentioning the elephant in the room. So we live in this strange yet super, super exciting era of generative AI, where we have language models that are at least potentially reshaping how we access information. As more and more research development and compute resource get poured into developing new variants of those language models, we see the performance of language models get pushed to new heights by incredible speed, at least on paper. However, despite all the hype and excitement, we're actually not seeing language models being widely adopted in many use cases in the real world. One of the key limiting factors, I would argue, that is language model by themselves rely solely on their parametric knowledge when generating the outputs. And they're oftentimes not that reliable. This will lead to practical issues like hallucination in the output, etc. And since the parametric knowledge cannot be easily updated after training, you would end up having a stale set of knowledge being encoded in the model, which makes them disconnect from what actually happens in real time in real world. So the general umbrella theme of this talk is going to revolve around the question of how do we use world knowledge to enhance language models' capabilities? And this theme connects to many of the challenges we have with language models in general today, such as identifying hallucination in model outputs, or alternatively, how do we ground model outputs to what we can trust out there? And also in inference time, how can we incorporate world knowledge without having to update the model parameters in real time when we use the language models? So a key observation I want to highlight here is many of these problems are actually not just limited to the scope of language models, but they also apply for human-generated text. So if we think about the problem of hallucination and the grounding or attribution of text I just mentioned, we've actually been fighting the same set of problem with human-generated text all along. We have been trying to find ways to at least identify mis or disinformation, or the more subtle forms of biases, such as political framing bias you will have, for example, in news articles. So these kind of biases, these kind of hallucinations could exist across many different information sources in a really subtle way. And to me, one of the key issues here is that we don't currently have a good data infrastructure that will allow us to compare and contextualize the information across different sources, which would help us at least identify, if not understand these issues. All right, so let's start with an example, just to see sort of what it takes for humans to contextualize and understand information in text. So here I have an example of a scientific claim about the empirical evaluation results of BERT. So immediately you will notice that the sentence actually tells us many different things. In this case, it implies at least five individual things just in this one piece of text. For the rest of my talk, I'm going to refer to such individual claims in text as propositions, which I'll give a more concise definition later on in the talk. Okay, now suppose I want to understand if any of these propositions or claims are true, or I want to find out the context in which these propositions are made. What I would do is I can actually try to find the places in, for example, in the original BERT paper that mentions the results. This will help us verify, okay, this statement is, this proposition is mentioning the correct results. But things often get somewhat complicated. So what's interesting in the BERT paper is that in a different place, they actually report a different number for the same model evaluated on glue benchmark. And different sources from outside, for example, this blog post from Hugging Face, would actually refer to different numbers from the same paper. So what's going on, right? Turns out the 82.1 number, which is different from what people typically report, happens where they exclude one of the test sets during evaluation in the glue benchmark, which gets mentioned in the background caption of table 1. So really, you sort of need to understand the context in understanding, okay, why do we have different results? Why do we have different answers to the same set of evaluation? And to really understand the whole picture, we'll have to sort of figure out, okay, how these information connect together and how do we, and in order for us to compare and contextualize the information we have at hand. So I want to mention that for this specific type of scenario, I actually see a really recent relevant paper from AI2 that sort of does this thing from, so that tries to support this feature from a different perspective that I am trying to do. All right, so this brings us to the theme of my PhD research, which is building architectures that could help human as well as AI systems to compare and contextualize information across different sources. So in early years of my PhD, I actually worked on this problem of trying to build a usable search tool from the user perspective for them to compare multiple answers, especially in the case of debate-worthy question. For example, during COVID, there were a time where should we be wearing masks? This becomes a sort of debate-worthy question with no single correct answer, at least at the time being. So I'm gonna quickly go over how it works. Basically, instead of what we do in normal retrieval engine, we actually look into basically the content of each document and try to identify the key one proposition that could serve as answer to the specific query that user types in. And instead of just showing you the top 10 relevant documents as most search engines would do, instead we organize the results based on whether they share similar answers or similar propositions when as a response to the given query. So we organize, basically we will show in parallel what are the different ways for which you can answer to the same query. And also we basically contextualize, so that we contextualize the answer with different sources, so users will be able to see, hey, these are how different sources mention the same things differently. So in terms of impact for the users, we actually observed that the user experience will benefit from the ability to compare different answers across multiple sources and having a more contextualized view of the whole picture. So we did the user study where we compared to Google search, where only the top 10 results are given to you as a ranked list of web pages. We see that, at least in this scenario, user would much prefer our system over what the Google search result that Google provides. So today, many commercial search engines start to support this feature as well, which is say to see the same type, at least the same type of feature. They could be implemented in different ways, but similar ideas has been adopted in different commercial search engines, for example, Bing Search, Niva, and Google Search as well. Okay, so hopefully this was a cool thing to show, but a more general goal that I want to touch on is, what if I want to compare really any information in one document with every piece of information from other different sources? So at least on a really high level, this could enable a lot of use cases and applications. For example, if you're a lawyer, you want to try to find a regulation that supports a specific claim in a legal document. Or if you're a medical professional, you want to know, okay, how do the clinical trial conclusions changes over time with respect to one type of disease or phenomenon. So coming back to the birth example, so if we take a step back and think on the real high level, so a sort of key requirement compared to how information retrieval or a language model work is that we sort of need a really fine-grained notion of what the basically what the document says. Basically, we have this need to query for the individual propositions in each document source when doing this type of operation. So the key idea here is really, instead of indexing information and modeling the relation between information as we do in normal retrieval systems, we want to model relations really on a more granular level of, as we mentioned, the proposition level, which is individual claim that each document makes. And our goal is really to be able to do, given one thing set in one document, we want to retrieve, okay, what are the other similar things or contradicting things that's being set in all other sources. So we want to be able to support that kind of operation in a sort of efficient and scalable way. Okay, before we jump into the technical details, let's start with a more precise definition of propositions. So this notion of proposition is actually a long-standing concept in computational linguistics and NLP in general. I won't go for the full history lesson here, but basically proposition conceptually means the individual units of meanings that you would have in one piece of text. For example, we have a really simple sentence right here: Alice and Bob went to the zoo. In this sentence, you would have at least two propositions where Alice went to the zoo versus Bob went to the zoo. So you can think of it as, if you want to verify the original sentence, there are two different things you would want to verify. So a conceptual question is, okay, why do we need to go into such granular level? Why don't we just, for example, index information on the sentence level? So first of all, in English text, what we found is more than 90% of the sentences, in English at least, contain more than one proposition. And in our previous study, we did a experiment where we look at, for example, topically related documents from English Wikipedia or news domain. So examples of this could be, for example, you have the same Wikipedia page, but one from English, the other from another language that's back translated into English, so that they will actually have different levels of details when they describe the same entity. So what we found is, about in such related document pairs, if you look at sentences from one document, about 46% of the sentences actually contain some information that's verifiable by the other document. And among those sentences, only 1 out of 4 sentences is actually verifiable as a whole sentence. And the rest 3 out of 4 are only partially verifiable, meaning that there are only some propositions within the sentence that can be cross-checked with the other document. So here, if you have a model, if you just check for example, those kind of semantic matches on the sentence level, you actually missed out on about 75% of all semantic links or matches across topically related documents or sources. Okay, hopefully by this point, I've convinced you that indexing text by propositions, this is really important. Tell me more, right? But first question, how do we actually parse text into propositions? So retrospectively in 2024, I can tell you that, okay, this breaking down text into proposition, you can do it relatively easily with language models, with few-shot prompting. And we'll go into how we evaluate this in a bit. So in past work, just to sort of create an evaluation set and understand what it takes to solve the problem, we created this data set from English Wikipedia and News, where we take 500 groups of 3 topically related documents in the data set, and we actually train human experts. We actually train them for a couple months before they start working on this, and then we ask them to exhaustively annotate all the set of propositions within each sentence within each document. So we ended up having a sort of large-scale data set for this proposition segmentation task. And also we have annotations where for each propositions within the data set, we have the annotators label its truth value with respect to another topically related document. So whether this specific proposition can be supported by the information from the other document. So a sort of important detail for which I'll explain why that matters later on in the talk is basically instead of expressing proposition in natural language, in this data set, we opt for representing each proposition by attention mask over the original text. So you will represent each proposition as the first sort of 0-1 token mask over the original sequence. And the benefits of this really quickly is this format gets to retain the full context of the original text when you use them as model input. And from a human annotator perspective, it is just easier to annotate with higher radar agreement compared to if you ask the rater to write each proposition in free-form text. And the most important reason I would say is that the token mask, the attention mask format, works really well as model inputs to the modern transformer-based language model we have these days. So compared to the more traditional notion of propositions that we had in NLP and computational linguistics, we found that it used to be the case where propositions are represented by this sort of structured proto-thematic predicate argument structure that we used to have. We are actually relaxing the structure a little bit and basically give it more freedom for what a proposition is. So we found that in practice, our method actually leads to more comprehensive extraction of propositions from text in general, with respect to different syntactic formulation of the sentence. Okay, so the goal is to use this data set to understand how well can we parse text into propositions with the current tools that we have. So I'm gonna just give the most important takeaways from this result. First of all, few-shot prompting with large language model actually achieves relatively good performance. And what's more interesting is if you distill the large language model to a much smaller sequence-to-sequence model, we actually see little to no performance drop from doing so. So that you can actually have a much smaller model that you use for inference to parse the text in a relatively large scale. And also, at least on our data set, we see that if you fine-tune a small model just on the set of human annotation that we have, the model actually gets somewhat close to human performance. But in practice, we see that since our annotations are sort of limited to only 2 domains, it doesn't generalize very well to especially when you have noisier text, for example, data from web forums in practice. All right, I'm going to pause here and see if anyone has questions up to this point.
A quick question.
Yeah.
Did you try fine-tuning GPTs by any chance? Or just
we actually haven't.
Okay.
Yeah.
Thanks.
So, because I think the problem is since we are the way as you will see it, with the way we want to use it is really to use it to parse a text on a real large scale. For example, the whole Wikipedia. Yeah, it just doesn't really make sense to for example, use something as large as GPT to directly parse the text. So that's why the sort of performance we actually care about is mostly on the smaller models.
Okay, thanks.
Yeah.
I guess I had one other question. Actually, could you jump back to slide 25 really quick?
Okay.
Yeah, so I thought this slide was very helpful. I guess, so your entire representation really is just these selected spans in, in the original sentence. So for example, the fact that 20-year-old describes the age of Anthony Bennett is like implied, and you and I know that from the highlighting in sentence 3.
Yeah.
But it's not actually an explicit output that the system is required to produce for this example. That is, the semantic connection there is not actually part of the output. You only need to identify these 2 related spans.
Right, that's true. So at least that's how this data set is formatted. But as we will see actually in practice, we asked the language model to recover basically the full natural language expression of each proposition when we use them in practice. So the reason why part of the reason why we go for this simple span select, like span markup format, is just from operational point of view, it's easier to annotate because we actually tried the other way around. It's really impossible to get annotated agreement in this case. So yeah, I'm not saying that the proposition should be represented in this way. I think just mostly for evaluation purpose and for the specific use case that we'll see later on, this makes sense.
Okay, got it. And then you'll post-process this, and yeah, I would imagine if you ask GPT to like express the relation between these spans or something, it would actually do quite well given the sentence. So
yeah,
fair enough. Okay, great, thanks.
Yeah. All right. Okay, moving on. So in the previous section, we see, okay, we can parse text into propositions, but I haven't explained why do we represent text as proposition, and how is it useful for language models? So we actually look at the case of retrieval augmented language model, where the goal is really, instead of just asking models to produce output based on its parametric knowledge, suppose we have a new set of knowledge or a up-to-date set of knowledge for which we want the language model to answer based off. We have this retrieval augmented language formulation where it's really simple. It's just you retrieve from a pre-processed pre-indexed corpus, and then feed the retrieved text as input as input prompt to the language model in order for it to derive the answer. So one of the common practice these days is you would use dense retrieval models as retrievers in the retrieval augmented language model formulation. So roughly the way it works is you have you have one or two neural encoders that each encodes the document and the query into the same vector space. And then you rank the documents by the similarity between the document vector and the query vector. So regardless how you instantiate the dense retriever, either by like if you have cross attention, if you have a different similarity function or not, a sort of common requirement or common assumption involved in process is you would need to index and process the retrieval corpus by some unit, because you have the way it works is really you encode some unit of text into one vector as one unit for retrieval. So with the common practice with dense retrieval is documents are typically indexed by some text segment, and most typically it's going to be 100. The whole document gets segmented by a 100-word window, or just coarsely by paragraph. And this is mostly constrained by the fact that the encoder model, the context window length of the encoder model is limited. So here we are going to ask one research question. So during inference, does the granularity at which you index the retrieval corpus actually affect how downstream language models will use and access the retrieved knowledge? So here we do a empirical study of 3 retrieval granularity from the perspective of asking language model to solve open domain QA with retrieval augmented language model. So here, an example would be if you ask the language model, what is the angle of the Tower of Pisa currently? So if you retrieve by paragraph or passage versus if you retrieve by sentence or propositions, here's roughly the different kind of things that you will get. So we will see that if you retrieve by passage, you end up having a longer context, which potentially contains more irrelevant information. And sometimes the irrelevant information actually contain like really strong distractors that the downstream QA models will actually be distracted by. And if you retrieve by sentences, what ends up happening is you sort of lose you would lose the necessary context information necessary to answer the question. So we end up, so here, if you retrieve by proposition, we end up asking the language model to, when they parse the proposition, we ask the language model to do this decontextualization step where they're expected to output the proposition in natural language form, and we ask it to add all the necessary context that's within the document to make each proposition standalone. So this way, even from a human perspective, you will imagine, okay, by organizing the knowledge in such a structured way, you will model ends up having an easier time to answer this question. And that's sort of what we see in practice. So we did this evaluation on using a off-the-shelf retriever without any retraining. So it's being pre-trained on, for example, DPR is being pre-trained on documents level inputs. And in the right case, a GTR is pre-trained on more data from different domains, so that it sees inputs from different varying lengths. But the general observation we see is that especially on data sets where the model hasn't been trained on, meaning that it hasn't seen the training split of the data set. In other domain settings, we actually see a sizable improvement from just by looking at the retrieval performance already. And if you look at when we feed those kind of retrieval texts from different granularities to a downstream language model to answer the question, we actually see roughly a similar trend. So we create a setting where we limit the compute budget, where we fix the number of retrieved tokens that we feed to the language model, so that retrieving by, for example, paragraph don't get the unfair advantage of just having more and more information when answering one question. So under this setting, we see that also in out-of-domain, when answering out-of-domain questions, we see that the retrieval by smaller units generally give you better performance. So looking closer to see where the improvements actually come from, we see that the retrieval performance actually improves for query with less common entities. So we looked at, on one of the data set, we looked at if when the question contains an entity that appears more versus less in the entire Wikipedia, how does the performance correlate to the frequency that entity appears in Wikipedia? And we sort of see that with less common entities, the performance gap between retrieving by proposition versus retrieving by sentence or documents grows larger in these cases. So this observation is important because the whole motivation behind retrieval LLM is we want the language model to really generate to long inquiries containing long-tailed information, and possibly in different domains. For example, when you ask questions in the medical or legal domain. Yeah. So at the same time, where do retrieval by proposition give mistakes? So we see that there are still many hanging questions that we can improve on. For example, when we ask language model to do this explicit decontextualization step, models aren't going to be perfect in it. I think Semantic Scholar also worked on this problem. So you're probably familiar with it to some extent. But basically, this question, this decontextualized question, is challenging, and also it can really be domain and task dependent in a lot of cases. But all in all, since this presents really a really simple enough idea, because you don't really need to update your dense retriever, you don't really need to update your language model. All we did was to change the way that the retrieval corpus index in order to see some performance. So in practice, we actually see a lot of this idea being well received by the open source community, presumably in the use cases on different domains, for example, medical and legal text. All right, so before jumping to the next part, any questions? Okay, moving on. So we showed that at least through a relatively simple and neat experiment, we showed that storing knowledge and access information in the form of proposition helps both retrieval and downstream inference by the language model. Now, can we actually build? It's still not quite where we want to get at. Can we actually build a proper proposition text retriever that works on the proposition level? So I'm going to tell you what the problem is. So before, in the previous section, what we did was we're not changing this dense retriever in any ways, meaning that it's being trained on either sentence level, paragraph level, or document level data. So the problem with these models is that these models are typically not trained to work on the proposition level in a way that, for example, there's a popular text embedding model called SimCSE. And the way it's trained is that you have two same sentence, but when you apply different dropout masks to them, the model is encouraged to assign similar embeddings to the two versions of the same text without two dropout masks. If you think about it, this is actually the opposite of what we are after. So ideally, what we want, given our goal, we actually want a text encoder to do the opposite. We want to have a text embedding system that, okay, given a piece of text, outputs k different embeddings that each correspond to a different proposition within each text. So compared to what SimCSE does, for example, and other text embedding model does, it's actually the exact opposite. So how do we address this problem? So we ended up having designing this architecture that actually looks very similar to how sentence encoder works. The only conceptual difference is that it takes, first of all, it takes an extra. So it works on, we designed the architecture so that it works on the token mask format of the proposition. And the way it works is we input for each sentence, we input the list of propositions to this model. And instead of, as opposed to what you see in sentence encoder, you would mean pull all the tokens and obtain a sentence embedding for the entire sequence. We actually have different, we actually pull for each proposition, we only pull the set of tokens that's in each proposition as the representation for each proposition. And before going to the next part, I want to mention that the token mask is only applied during polling, not on the encoder, meaning that the encoder actually sees the full context of the original text. So that you can think, conceptually, you can think of it as a version of contextual text embedding. So the way we learn the encoder is we actually use an in-batch supervised contrastive loss that sort of resembles the high-level objective that we are after. Given a mini batch of sentences, each sentence will contain multiple propositions. We designed the learning objective so that it learns to recognize which two propositions across different sentences are actually positive instances of each other, meaning that they imply similar meaning from different but matching contexts, basically. And what's interesting here is each proposition within the same sentence, presumably they imply different meanings because they are different parts of the sentence. The objective will naturally push them to have different representations, meaning that they will have low similarity score. So we are able to basically operationalize and write the whole bunch of code to make it work really, really nicely in a distributed learning setting. So it's like scaling up is easy with this kind of learning objective. All right, so next basically it's a general architecture that works on any subtext to subtext pair of data. But just for our use case, we create training data in a way that we start from unlabeled sentence pairs, and then we distill the proposition level label, meaning what are the set of propositions between these sentences that can match with each other from a natural language inference or textual entailment model. Basically, after we decompose the sentence into propositions, we use an NLI model to check if each pair of propositions are sort of semantically equivalent by bidirectional entailment operation. And then we convert each proposition back in natural language form using a heuristic where we find token matches in the original text versus the each proposition expressing natural language. So we use this kind of data to supervise this sub-sentence encoder, and we evaluate this by on the prop segment data set I introduced, but we reformatted the data set into a retrieval problem where, given a proposition, you want to retrieve the set of relevant or things that can either support or contradict the proposition from other topically related documents. So given each proposition, you will need to select one or two such proposition from a candidate of 45K from 1,500 documents in total. So we see that if we compare it to the baseline of sentence encoder, where it just do nothing sophisticated, but basically encodes the set of tokens, learns to mean pull the set of tokens that's within each proposition. We see that by having this contrastive learning objective on the more fine-grained level proposition, give us much better retrieval performance on this task. And what's interesting is the system actually works as a sentence or document level dense retriever out of the box. So the way it works is we sort of score each document, sentence by the highest scoring proposition within it. And we see that it's very competitive compared to if you just take a sentence or document level text encoder and do retrieval on these level respectively. Yeah, one of the cool thing I want to mention is the we see that by training the model this way actually generalizes to inputs that are not necessarily shaped like the proposition that we have. So we evaluated on this conditional semantic text similarity task where you're asked to judge the conditional similarity based on just the one aspect, one condition of these two text inputs. All right, without going into too much detail, here's what basically some of the broader impacts of what the whole setup that we have. So we see that in practice, we see that this whole setup can help address some of the tasks that wasn't possible with models that work on just more coerced level of things. For example, when you have a proposition level embedding model, and sort of entailment model, what you can do is you can detect hallucinations in text generation model by checking, okay, if each proposition in the generated summary can be verified in the original document. And combining the inference result from each proposition, we will be able to infer what set of spans within the generated summary or generated text in general is hallucinated with respect to the document. So the message I want to send here is that representing textual knowledge at proposition basically creates more opportunities for us to infer the semantic relation between text that wasn't quite possible before with our other models. So with this architecture, we sort of, at least in part, achieved what we set out to work on, right? So I want to mention, before wrapping up this part, I want to mention that the architecture itself can actually be applied to any pair of subtext to subtext training data. So it's just that in the paper, we instantiated with one kind of training data. So at least conceptually, the architecture can be used to solve many text-to-text linking or retrieval tasks, such as entity linking, citation, attribution generation for text, etc. Okay, before I jump into future work, any questions up to this point? I can also take questions when I finish the whole thing. Okay, cool. So moving on. So what's in the future work, right? So if we take a step back and circle back to our big picture goal, we're actually still very far away from the goal of comparing or accessing any kind of information in one source to everything that's out there. So for example, especially when it comes to the scientific domain, we still don't know how to access many of the knowledge that we humans will know. So in recent work, we collected a data set where it contains many different questions that you would ask in your professional work setting about really like what people are interested in different fields of science. So we see that models these days, it doesn't matter if it's a language model, it doesn't matter if you attach a retrieval system to it, it doesn't matter if you use a retrieval system to sort of check for its factuality after the language model provides its output. We actually see that in a lot of the cases, the model actually hallucinates when they are asked to provide those scientific knowledge. So even the best model hallucinates more than 30% of the time. And when the models happen to give the correct answer, most of the time it was just from sort of a wild guess. And it cannot consistently find a reliable explanation or attribution for what it has output. So the broad theme of what I'm interested in working on next is, can we actually teach model to reliably retrieve and infer over scientific knowledge? So I'm going to talk about an ongoing piece of work that I'm doing right now. So we start from the sort of motivation that many of the, especially scientific knowledge, we actually still don't know how to access them, even though from a human perspective, we know that we have those kind of knowledge. So here's an example. Suppose you are you do research with respect to orchids, and you want to see, okay, I want a system that show me, okay, what are all the orchids that can be found in Indonesia and Malaysia, but not in Thailand. So this is so if you have a structured knowledge base that contains all the information, okay, congrats, that's easy for you. But for most of the cases, you actually don't. So the question we were asking is, okay, just with all of the free text knowledge we have online, can we actually correctly query for those kind of knowledge? So very quickly, as expected, language model cannot really do this these days. And even if you relax the constraint and don't ask the model to enumerate all of the things, it still doesn't work. It basically doesn't know how to respect these kind of Boolean logical constraints that you will have when querying for scientific knowledge. So suppose we ground our setting into just retrieving Wikipedia entities that can satisfy certain attributes that involves logical operations. We see that current models, especially dense retrievers, they just don't know how to respect those kind of constraints. Meaning that if you have a query that asks for attribute A or B versus A and B, the model simply doesn't respond to the change of the logical relations in that category. So the general idea we are going for is we want to train a retriever so that it works in a more structured and logical way. So in this case, suppose I have this kind of query that we know that can be parsed into some logical form where each subquery is the variable, and you would have logical relation that composing the subqueries. We want to, on a high level, want to learn the retriever to use compositions of soft and differentiable Boolean operators instead of just the dot product over the entire query between queries and retrieval candidates. And the general goal here is to sort of make retrievers work like the traditional knowledge base that you would expect from, especially in a scientific world, where there's a sort of high requirement of you reliable retrieving knowledge based on the logical requirements that you have. And sort of the implication of all of what I said, especially the representing knowledge by proposition part, is it creates a lot of opportunities for which you can potentially do inference in a more symbolic way. And one of the direction I'm very excited about is it sort of creates a way for us to amortize inference over this kind of neurosymbolic knowledge structure. So just very briefly, the sort of thing I want to go for is, suppose you have observation and you have expected outcome. And you're looking for sort of the scientific explanation or set of knowledge that can explain this outcome. So with language model trained on maximum likelihood training, you can't really do this kind of posterior inference to sample over the space of explanations for you to figure out, okay, what's going on. But if you abstract those set of explanation, those set of knowledge into proposition in a symbolic way, you can potentially do a lot of things to make that happen along that line. So yeah, I think many ideas, many possibilities. What I've been doing is, I think, echoes very well with what semantic scholar is thinking as future steps, and I'm happy to chat and brainstorm for more ideas offline with all of you. All right, so these are the list of papers covered in the talk. These are like more publications from me that I think could be related to the materials in the talk here. And I want to thank my collaborators, plus many others not shown here. Thank you. I hope we reach the moon one day in this line of research.
thanks, Sihao. So we have a fair amount of time for questions. And maybe I'll start with one while people are thinking. Let's see. I guess I'll ask a quick question about the future work direction. So, I think getting retrievers to behave, or getting retrievers to handle these logical operators is a great goal. There's a technical challenge there in that it's often possible to get good ranking performance out of retrievers, but not as good of like classification performance. So once you want to know, is this an orchid that's in both, let's say Malaysia and some other country, but not this other one, that retrieval models might be really good at ranking orchids for, from those more likely to be in Malaysia to those less likely. But it's harder to determine where the ones in Malaysia sort of begin and end, like drawing a threshold in that space.
All right.
And as soon as you want to be able to do composition of multiple logical operators, you actually have to know right where that threshold is in order to know how to like balance the different components of the of the composition.
Right.
So yeah, I guess what are your thoughts on how to solve that?
Yeah, I think so. I only mentioned retriever, but the same sort of basically, if you think about if you use a retriever to do candidate retrieval, and then you do the classification to determine the threshold in the next step, the challenges involved are actually roughly similar in both cases. So the obvious prerequisite is you sort of have to have the notion of proposition for which you parse the query, the requirement into smaller pieces, and you sort of do this semantic parsing to figure out what's the logical relationship between them. So basically, I think, just in my head, just train a retrieval model plus a re-ranker or a classification model in the same amount of data. It's just that in retrieval, you train it to do this ranking, and in classification, you have this binary label indicating whether it satisfies the requirement or not. But either way, I think just having this notion of proposition will help greatly in both cases, right, to happen.
Got it. Okay. When the re-ranking step, like I guess the only drawback there potentially is efficiency, right? That you have to re-rank too much.
Right.
And if you could somehow solve that at the retrieval stage, that'd be really exciting. But okay, sorry, I'll pause and let other folks ask questions. Although I won't pause for that long because I have other questions. So slide, let's see, can you go back to slide 45 really quick?
Okay. 45.
Oh, sorry, I guess it was 47. It must be.
Oh.
What is going on? Was there some animation on this slide? Like a box that comes in?
Oh, right. Yeah.
Yeah, there we go. Thanks. Thanks for jogging my memory. This is an interesting design decision in the green box. So, you might imagine the model, if it were somehow informed of what the proposition is, it might end up representing, the tokens of that proposition differently.
Mm-hmm.
So, I mean, can you talk to me a little bit about the trade-offs of this decision to basically not tell the model what proposition it's encoding and only enforce that at the, in the loss?
Yeah, this is a actually a very interesting question. We actually compared to both cases, and what we found is with smaller models, it's generally better if you enforce the encoder to also just see the tokens in the proposition. But when the model gets bigger, when the backbone-based model gets stronger, it's actually empirically better to have the encoder see every token there is. So my hypothesis for this is even though you're not providing in the encoder stage, you're not providing the proposition explicitly to the backbone encoder. Stronger model, assuming that they are more bigger model, they are more expressive. They actually sort of learn just from the loss supervision from the loss signal, the notion of proposition, so that it knows how to encode token differently, even though the proposition that are not provided as input to in the encoding stage. So yeah, that's a really interesting observation that I didn't mention in this slide.
Okay, yeah, thanks. I guess, sorry, did you try a variant that like flagged the proposition to the model? So like not masking the non-proposition tokens, because like those are very useful.
Yeah.
But just maybe delimiting the spans or doing like some additive embedding to indicate which tokens were in the proposition or not.
Oh yeah, I see. Yeah, that's a good point. I haven't tried that. So mostly, part of the reason we go for this design is also efficiency, because you can only do so for multiple propositions within one text. Especially, you are talking about propositions in a paragraph. You just need to do one forward pass for the encoder. But yeah, I think just in terms of performance, I think your suggestion might bring better performance, I think.
Interesting. Yeah, the efficiency point is a good one. All right. Any other quick questions?
I have a quick one, but I'm not sure whether it's super relevant. So it seemed like this task you are talking about how to like deconstruct different contexts, or like in this case, proposition from a couple of texts, right?
Yeah.
Is there any thought about how to infer some fact or possible claim by combining contexts together?
Right. So I guess part of what you are saying is if there are implicit things, how do we sort of recover the implicit things that are not obviously stated?
Yes.
That I think first of all, it's important, right? Because especially depends on what the downstream task is. It's kind of important that these are also like missing context that you would want to add to. I don't have a very good answer for that. All I can say is I think. So I would sort of think language model is suitable at, if executed well, language model could be used to recover those kind of missing contexts. And I would imagine if you sort of tell the model explicitly what are the propositions are, it could steer model in a direction where it better recovers what the implicit ones are, basically. That would be my guess. But yeah, I don't have a super well thought out solution for that problem just on top of my head.
Got it. Thank you.
All right. Well, it looks like we're at time. Let's thank Sihao again. Yeah, thank you, Sihao, very much for the nice talk.
Yeah. Thank you so much. Thanks everyone for having me and then the great questions.
Bye.
Yeah. Bye. Thank you.